Okay, next up is spreadsheet modeling. Now, I'm going to lay my cards out on the table here and tell you up front that this is the tool that I have made the most use of in my decade-plus long career, Excel in particular. The most sophisticated Excel models I've developed priced winning bids in public energy supply auctions that banked the development of $1 billion worth of new renewable energy infrastructure out in Chile, as well as closing a $400 million plus deal to build and refinance another wind energy portfolio out there. These tools contain numerical solvers that I coded for myself in VBA, and they imported simulation data calculated by other specialized engineers who provided energy price forecasting at different spots on the grid, as well as simulations of variable weather outcomes that could impact our renewable energy plant performance. All of this was being done to calculate a relatively small set of magic numbers for the private equity principals to make decisions with. Now, all I'm saying with this not so humble brag here is that I really know spreadsheets and I have experience to defend what they can do and also be realistic about what they can't do as well. The good news for all you tokenomics pros is that the problems that are a good fit for spreadsheets to handle almost certainly won't be anywhere near as complex as what I've just been showing you. That kind of complex modeling that I was talking about is actually quite peculiar to the heavy infrastructure niche that I used to work in. I've seen large real estate deals get by with much, much less. And from what I've seen in blockchain, spreadsheet modeling for blockchain startups is on a similar level of detail to the modeling that I see being done for conventional startups, which is to say, pretty light. The model's building blocks aren't as complex as what you need to build a fully integrated financial accounts model. Generally, it doesn't make sense to invest in a super detailed model for really early stage projects that are prone to loads of unknown factors. And these projects are also funded by capital that has a high tolerance for risk, which removes some of the need for that intense modeling. In these situations, we see the spreadsheets being used to develop some quantitative reasoning around the project and its business plan, and to do some general stress testing and scenario exploration to create watertight narratives to pitch with and to provide a solid point of departure for financial and business planning. Now, when blockchain projects get to operational stage, my bet is that spreadsheet modeling will continue to offer value in these phases as well, much in the same way that it does for financial planning and analysis roles in conventional business roles, although almost certainly in complement with some analytics software capability, which we'll cover later. Even seasoned game economy designers sometimes express a preference for using Excel over other specialized tools like machinations, and data scientists in all industries frequently use Excel as a prototyping and rapid exploration environment. But yes, spreadsheets have a bad reputation. Let's look at the two most common complaints. First of them is that spreadsheets are messy. The software has the unfortunate convenience of being a tool that anyone can use, while also being incredibly easy to make a complete and utter mess with. The remedy to this is to build your spreadsheets following some simple but rigorously applied design principles, analogous to the good coding principles that professional developers are trained to follow. This allows you to build tools that are maintainable, less error-prone, and fully appropriate for design, exploration, and insight extraction in many design problems. The other complaint that a lot of people are stuck with is that Excel is a really slow platform to develop with. That's just because they've never seen a real spreadsheet jockey in action. Those of us trained in the investment banking culture were taught never to touch the mouse. And there are even contests for this skill set out there. If you have a spreadsheet engineer who's properly trained, you're going to get some really cool advantages too, including the opportunity to support development and communications processes that are inclusive for non-technical stakeholders who can use their business experience to spot flawed assumptions or suggest other failure scenarios to test. To be able to do this, a well-designed tool should make clear distinctions between the assumptions being made and their outcomes, and the calculations need to be laid out in a readable visual format that's optimized for error reduction, audit, and inspection. This gives you a tool that allows you to make on-the-fly exploration of different scenarios and possibilities with non-technical decision makers in the same room. Indeed, if you need to express your results in the language of financial accounting, which professional CFOs and investors are trained to read, a spreadsheet is likely to be the tool of choice. Okay, so obviously I'm a spreadsheet fanboy, but give me a chance at being even-handed and balanced here. When are spreadsheets not the right tool? In my opinion, I think we're still scoping the exact detail out here. It's too easy for data scientists and engineers to scoff at spreadsheet tools just because they are simpler and more restrictive as a modeling environment without bothering to offer details about what components, system types, or evaluations specifically are not well handled by a spreadsheet modeling framework. I don't think complexity is a clear criterion to go on either. Multi-million-dollar decisions by external investors and internal managers of the largest companies on the planet are guided heavily by accounting data. That's the analytical framework that did most to drive the use and adoption of spreadsheet software. These are very complex companies and handle a lot of valuable resources, so the stakes are very high. If accounting was woefully inadequate in the data science age, we wouldn't still be using it to guide so many high-value, high-stakes decisions. But I do fully agree that this style of modeling has limits to its reach, and I'm going to have a go at stating what those limits are. Imagine we want to model a car manufacturing business, one that has a really high-tech automated assembly line like the one shown here. If this high-tech assembly line uses known and established technologies, I can make a reasonable model of the economic performance of this business using accounting data from similar businesses. I do not need to model how the assembly line works. The information about the reliability and the performance of this machinery is already captured and represented in a high-level way within the accounting data that I'm modeling with. But now let's consider an alternative, a case where we want to roll out some entirely new kind of car assembly technology, something radically different. To include information about the differences this technology brings to the bottom line, we need direct modeling of that machinery's performance. And that's a complex system with many parts and many points of failure. Excel is not up to the job, 100%. Of course, engineers could calculate parameter values that then plug into a spreadsheet model, but that's different. The spreadsheet is no longer a complete tool there either. So in terms of this analogy, spreadsheeting is the wrong tool when the analysis or brief requires us to evaluate the performance of some complex machinery. But where I think this analogy is unhelpful is that it strongly leads us to think that this is a question of scale or detail, which I don't think is quite right. What's actually material are the kinds of failure events that we are trying to evaluate with our modeling. If we're evaluating the risks and performance of a large multi-million-dollar business, it can break in many ways, but the break generally happens at some known boundary. Sales falling, costs rising, tax policy changes, cost of capital increasing, slow growth, and so on. In some sense, we don't need to worry about what happens away from those breakpoints at the boundary. The company continues to function. Whether it does so to a better or worse extent is of interest, but fundamentally the business operation continues holding together as a going concern. However, if we are evaluating a system that can break in more complicated and non-trivial ways due to unexpected combinations or sequences of events that may occur away from the obvious bounds of failure that we can determine in advance, I think we have a well-motivated reason to reach out for more sophisticated tools and frameworks. Let's bring back our DEX as a familiar example. Now, this system is much more akin to an active tokenomic machine, one that has multiple moving parts that furthermore depend on the actions of agents that are not necessarily coordinated with each other to shared ends. Now, this is a really important difference because that's something that a company does not have to deal with. It coordinates its labor and resources using employment norms and contracts. So here, I do think that the modeling of the details of this machinery through specific events and agent interactions is material to making an informed and comprehensive evaluation of this system. You may find yourself needing to conduct rich statistical analysis of stochastic factors, step-by-step simulations, or possibly optimize your design with the help of calculus, linear programming, or other advanced numerical methods. Spreadsheets are definitely not the choice tool in these circumstances. So let's now take a look at what some of those better tool options are.